Still with this same section, we just talked about the derivative of e to the x equals e to the x, which means the integral of e to the x is also e to the x right there, okay? But what we gotta do is just gonna do a few integral examples there. We gotta be really careful with the balancing. So here's like the new property I would kind of write down with my notes there. If I have the integral of e to the u, we're gonna get e to the u. But before you do that, you gotta make sure that's like a single letter right there. So we have to be really careful with our balancing. We'll talk about this in a second there. But a real basic example, if you integrate e to the 3x, you don't get e to the 3x. You got to be careful with your balancing, right? So if I have a weird exponent, something other than just a single letter, I'll let the u equal that power. And then we do the derivative of that, we're going to get 3. Balance that 3 with the 1/3. And now your u is equal to that power. So the e is still there, but your u is equal to that power. So now you have e to the u du. And now remember, here's our new property. When we integrate e to the u, we get e to the u, and then you're going to plug your x's back into the problem. Remember your plus c because we have an indefinite integral, and then we're done. So what I want to stress here, there's really two approaches that you're going to take on the e problems right there. If you see a single e in your problem, most of the time we're going to let the u equal that power, and that's going to work out perfectly fine for us. If you don't have a single e, if you have multiple e's in the problem, what I'm going to let you do is, like, it's not going to help us on this problem to let u equal the power. Okay, we're not going to let u equal the negative x or the positive x. You're never going to let u equal x anyways. But even if those are like 2x's or 4x's, you're not going to let u equal just the power when you have multiple e's in that problem right there. So that's typically my mindset on these. If I have a single e in the problem like I do on these, I'm going to let the u equal that power. Hopefully that'll work out for me. If I don't, then I'm still thinking about my normal tendencies. If I have a parentheses or a square root, let it equal the inside of the parentheses of the inside of the square root. You know, if I have a weird looking numerator, a weird looking denominator, I'll try to let u equal that whole entire denominator first there, okay? So, but it's not going to be just a power there. So I'll let it equal like the whole denominator, the whole inside the parentheses, or whole inside the square root, or the whole like e to the x plus 5 or something like that, that actually contains the e part of the problem. All right, so like right here, if I have a single e in the problem, I'm going to go ahead and let u equal just that power. And I'm actually just going to rewrite that as 1/2 x cubed. That's the same thing. And so when we take the derivative, we're just going to multiply by the power, decrease the power by 1. And then notice I got an x squared dx. Right there, I have an x squared dx. So that stuff is matching up, have an extra number. So we'll balance that with the reciprocal. And then remember, all the squiggle stuff is handled, and your u is just that power. So the e is still there. My u is just the power. And that's why that works out really nicely, because then you work into this problem like that main property that we're learning right here. So when you integrate e to the u, you get e to the u. Now, if I have a definite integral, numbers attached to there, then I have a choice here. I can stop right here, and I can use this initial u part, and I can just plug in those x's to figure out what those new u's are going to be, or I could plug my x's back into the problem. If you plug your x's back into the problem, you would use the original numbers attached to that integral there. So this would be e to the x cubed over 2. And I got my plus c, and then we're done. All right, so on this one, when you don't have a single e in the problem, not going to help us to let u equal any of those powers right there. So when I'm looking at this guy, before I let it equal the whole entire denominator, I'm not going to do that. I'm still going to try my normal stuff. So I see a parentheses. My mindset here is, let me try to let the u equal the inside the parentheses, and let's just see what happens, okay? All right, now, so when I take the derivative of that, tons of u du here. So when I take the derivative of e to the x is e to the x. The derivative of the negative x is e to the negative x times by the derivative of negative x, which is a -1. So we're going to get this. Now, as you compare these don't quite match up yet, but if you do a GCF with this original problem, if I pull this 2 out and just do a simple GCF right here, look what happens. There I got the e dx minus e to the negative x, there I got the e dx minus e to the negative x. So I got all that part that's being squiggled, so that matches up, so that stuff is handled. Now, there is no extra number in the du, so there's nothing to balance. This too is already part of your problem. So since it's already part of the problem, you just pull that out in front. And then remember, your squiggled stuff is handled, so you're going to substitute for the rest of it. So you're going to go 1 over your u is the inside of that parentheses, so that becomes the u. And then you still got to remember that that thing was being squared right there. So that's why I don't let it equal that whole thing being squared, because if I get a 1 over u squared, I can handle that. So But that's what I try to mean by let it equal the entire part, because just let it equal a power, not going to help you on that. And then this is just a u to the negative 2. So when you integrate that, be careful there. You're going to add 1 to the exponent. You get u to the negative 1 divided by that same number, divided by negative 1, carry down the 2. So this would be a negative 2 over u. And then you'll plug your x's back into the problem. And then you got your plus c. Then we're done.